Okay. So we will continue on this boson fermion business with the creation annihilation operator, and I hope everything was clear from the last time. So here we today we will go over the fermionic operator and go over some examples of it. Okay. So last time we finished by saying that we gave the prescription to create the Fock space of bosons by saying that so the Fock space states are of course described like this. And we said that I have an operator Bk acting on this n1, n2, nk and giving me root nk, n1, n2, dot, 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 nk minus 1. Oh, why does the AC doesn't turn on? Let me try it once. Anyways, then I stated there is a Bk dagger whose job is to create one particle at the k plus 1th at the kth state. And then we asked you to check that, and I also showed actually that this Bk dagger minus Bk dagger Bk is when acting on this nk state will give me 0, and that means they satisfy the algebra. Okay, then we also stated that this thing is actually delta kk prime, and all other operators bb and bk dagger bk prime dagger are 0. Okay. So everything was clear till now, I guess. And we also stated that we can show the structure of the Hilbert space or structure of this Fock space in the way that I state that I have some grid. So let's say I have only two states and I represent them as points in this space. And these operators basically takes you from one point to other by connects all the points in this space. Okay. You need not draw it like this, but in this case it helps to draw it like this. So it can either go from here to here like that, or it can go from here to here in some complicated path. And then we can express this in terms of the appropriate number of creation and annihilation operator. Then I pointed out that these things are different for fermions, and so what is different? So for fermion, clearly, so let's say I am starting to put fermion in these levels, and so this is level 1, 2, 3, 4, etc. And let's say I do this thing, put 3 particles, one at 6, one at 4, one at 2. Oh, one more point I just wanted to remind that all these states, all these points you can represent as some operator acting on vacuum. Okay? So it could be you can write it as B1 dagger, B2 dagger, 0. 0 means 0, 0, 0. So this 1, 1 is basically this. Or it's not unique because you can do another set of operation and get still the same thing. Okay. So this is a alternate way to represent this state, and I will show you today that what is the advantage of doing it like that. Okay. But before going to that, let's go to the fermionic problem. So let's say I am doing I am filling these fermions. I am trying to reach one of the fermion state in this way. I do a 6 and then a 4 and a 2. But I could have done this also. I could have done first a 6, then a 2, then a 4. So are these two things same? Comments?
No, sir. No, sir.
They are not same. Why?
So can you please repeat again the question?
Yeah, my question is, let's say I want to put particle in this level. So let me name it 1, 2, 3, 4, 5, 6. Now I want to put it in a order that I do it first 2, then 4, then 6. Or I could do it first 6, then 2, then 4, then 2. Or I could do it in this way, first 6, then 2, then 4. Are these two things different or same?
So they should be same.
Different.
Okay, what is the reason for saying same?
So because they're indistinguishable. So
Okay, and what is the reason for saying it is different?
Because they follow the anti-commutation.
Okay, but why? How it is exactly making it different?
When we put when we shuffle the states, means A4 and F6, it will provide us a minus sign.
Yeah, but think about from a perspective. Don't think mathematically. Think it as a physical problem. So let's say I gave you an empty system, empty set of states, and ask you to put particles. So if you put it as 6, 4, 2 and then 6, 2, 4, don't go behind the mathematics, right? Mathematics will follow the physical intuition. So what is the physical intuition, that should there be same or not? What's the
now I think
difference?
they should be different.
Okay, why?
Because since it's anti-symmetric, exchanging two particles will give us that minus sign because pair permutation symmetry.
Yeah, I understand the exchange. Okay, so anyway, so you are all going to the mathematical structure, but what I'm trying to say that this information, that what you have done before, the existing configuration matters, decides that where you can put the next one, because it's Pauli exclusion. So Pauli exclusion tells you if you put 6, then you cannot put 1 in 6. So your available space have changed. Then if you put a 4, then it says you cannot put anything in the 4 anymore. 6 and 4. So the available space is 2. So similarly, when you do the opposite way, first you put 6, then it says okay, 6 is gone. Then you put 2, then you say 2 is gone. So when you are putting the third one, you are acting on a set of states where how it is filled already will decide that where you can put the next particle. That doesn't happen for boson. So these two things are not equivalent. This is the physical picture. Of course, it is anti-commutator, anti-symmetric, but this is precisely the structure of that. So that means if I have to write these corresponding things, okay, if I have to write this, so I have changed the notation a bit. Yesterday I was using A for boson, F for fermion. Today I am just doing B for boson and F for fermion. So now I want to incorporate this fact that what is already filled will matter, that what can happen. Now of course if I flip it, it gives a minus sign also. So the way to incorporate that is following. So then your fermionic Hamiltonian, your fermionic thing will be, is it visible? Yeah, it is visible. Okay. So the way to write it is Fk. Notice there is no n1, n2, nk. It is a 0 or 1, right? So let's say I have one particle already in, so we know that if there is no particle, the Fk will destroy it and give you 0. That's how we defined it. But if I have one particle at kth level, it should destroy that, right? But while destroying it, it is not just this. There has to be something else. So not the normalization factor, because you know the normalization factor is trivial here because the possibilities are only 0 and 1. So there is no such complication here. It's just 1. So then the factor that comes here is this. So if you write the levels as, so there is a bit of subtlety here, but let's assume I'm writing it all from bottom to top. So it will say all the levels that is filled below that level where you are trying to put the particle. You have to sum over all the population of that and do and then put a minus factor to minus to the power that factor. So similarly, Fk dagger So let's first see how it works, and then we will discuss that what is the subtlety and why that doesn't matter. Okay, so this is the equivalent rule for fermionic operators. Now you will ask that, okay, then what about the point that
Sir?
yeah,
Is it -1 to the power k minus 1 k? It's not.
I equal to 1 to k minus 1 sum of ni.
Okay.
Is it clear?
Mhm.
Yeah, so I is equal to 1 to k minus 1 up to k minus 1. So kth level before the kth level, till before the kth level, and then that is why I am stopping at k minus 1. So now you want to check if this is true. So I want you to take this as an exercise that proves that, just like the way we proved it here. First do this much. So if this is true, then show this. So this minus sign will take care of this minus that you will introduce here. Okay. So prove this as a homework. You just need these two definitions. You need nothing else. Okay. So now
Yeah.
let's see how it works. Yeah.
Yeah, if we put a particle in 6 first, then it is checking the number of particles below that level. But if I put, I mean, is it the reason that the lowest energy states will be filled first, or so?
Yeah. So when you put the first particle, then there is no problem, right? It's when we put the second particle, then the information matters, right?
I mean, if I first put 6, then put 2, then while adding a particle in 2 will not be affected by the fact that there is a particle in 6.
Yeah. So that is the point. So here another subtlety is there. It is the ordering. So how are you going to order it? Okay. So let's first show this example. Let's first do this example. So this was okay. So this is to show that these two will be obviously different, and you can see why. So I should have written it like this. Okay. So this 0 0, if I put 1, so there is no sign here. Then I put the second, then there is no sign here either. But if I put it 0 here, no sign here. But if I go from here to here, then there will be a sign, because the left side is already filled. If I have written it in this way, if I choose the left side to be the lowest one. So I can diagrammatically represent it as this. So you go here, no sign, go here, no sign. You go here, no sign, but you go here, you are opposing the arrow. That means there is a sign. So if you want to put make such a diagram for fermions, such a grid diagram, it has to have a arrow, it has to have a notion of direction, that you are going in this direction, you get minus sign. If you are going that direction, you won't get minus. So think about it. This could be a very interesting formulation, a very interesting way to think about the fermionic hopping. Okay. Now, there is one bit of caution, that I have never seen that this way of doing it. But of course, thinking as this problem as a grid hopping problem is common, but thinking it like that exactly, that I'm not so sure. So one might have to do something a little more. So in this case, it is very clear that will happen. But if you have a high dimensional space, which means not 2 levels, many levels, then this picture is not so clear. Then one have to think carefully. That is why take it with a bit of caution. This picture is certainly correct, but whether you can extend this picture trivially to a higher dimension, that needs a bit of thinking. And actually, one of you can take it up as a term paper project, that how to formulate the fermion problem and boson problem in Fock space as a lattice grid hopping problem. Okay, it's a geometric problem. Okay, now this question. So there must probably, this looks like something weird. Yeah.
Yeah, then from going to 10 to 11 should have a negative sign, because it has a particle in the lower state. If I assume that the left side is the lower
Yeah.
state.
So if you think of left direction,
Hmm.
then you put this as flip sign and this as this.
Okay.
So it depends. There is a bit of subtlety there. That is what I'm trying to say. That how you have ordered this. But the good thing is that even though the sign changes because of that, at the end, whatever you want to calculate, the matrix elements, etc., that will not change. So that you can check.
Okay.
The physical observable, none of that change, even though you are defining it in this way or that way. Now this example. So let's try to see if I have messed up anything. So this is my ground state, 4, 5, 6. Okay, 6 zeros. So then I am acting F6. So let's say I have chosen to write it in this way. 1, 2, 3. Yeah, just the way you said, 4, 5, 6. So F6 should count the number of state on this side. So you have all 0. So what you get is 0, 0. Okay. Then you act F4. So you get 1, 0, 1, 0, 0, 0. Then you act F2. Okay. So now if I do the other way, yes. So the other way is following. So let me draw it here. So this is clear to everyone, right? Any comment?
Yes.
What about others? And why that yes is so faint?
Sir, can you write it in other board? Means
Are you not following what I have written here?
no. I think it's out of
No,
range.
it is clear to me.
No,
It's
for
out of
me,
range?
I don't know.
No, it's clear for me.
Okay, so maybe yeah. So since it is clear for someone, or how about someone else? Can you see it?
Sir, you just have to change it to spotlight mode so that you can see the full screen. Otherwise, it gets cropped. Not you,
What
but
is
whoever can't see it, the right side of the board, just change it to spotlight mode on your
Oh,
Gmail.
perhaps make it full screen. Or
Yeah, full
spotlight.
screen in spotlight mode.
Yeah. So I am acting. So how should I go from here to here using this rule? Okay. So let me repeat the statement. So my rule is I will count all the filling on the left side. Okay. So I counted all the left side, nothing is there. So I just put a 1, no sign. Then I want to act 4, F4 dagger on this. Okay. So if I act f4 dagger, I put a 4 here and nothing is on the left side. So no sign. Then I put 2, nothing on the left side, no sign, no issues. Everybody is on the same page? Comment yes.
Yes, sir.
Yes.
So now can you see why it would there will be a minus sign if I do first 2 then 4? So if I do first 2, then what will happen? Right? Now if I act 4, then there is already a 1 here, right? So I sum it up and put a minus sign. Everybody clear? How I apply this rule? How I apply this rule for this configuration?
Yeah.
Okay, anybody who is unclear about it? Actually, that should be the correct question. Okay, very good. Everybody is clear. Good. So now let's go to the. Yeah, I hope it is not clear because you are not saying anything because you didn't follow anything from the beginning, and it is because you actually followed it. So there are two kind of scenario where you let's say you followed everything up to n minus 1th minute and then you don't follow something at nth minute. Then you say, okay, I don't understand. But if you have not followed anything from the beginning, then you say, what's the point of saying anything anyways? So I hope that the latter is not the case. The former is the case.
So can you say
Okay.
that again if I add F2 again? I mean
Yeah,
F2 dagger first and then F4 dagger.
Yeah. So why it is a minus sign?
Because there
So
is
after
one
this-
particle in front.
Yeah. So now I am acting F2 on this. Okay. So what will I get? Right? Nothing on left side.
Yeah.
Now what happens if I act F4? Can you say?
Yeah, there is one particle, so there will be a minus sign 1 0 1 0 1 0.
Okay. So this fact that these two things has an exchange minus sign, that is already inbuilt into the property of the F operator, the anti-commutators. Okay. That is what. So it is already inbuilt the way it is defined, and it is already also inbuilt. If I shuffle these two operator, it will pick up a minus sign because of the anti-commutator. Okay. So everything makes sense. Now let's see how it is useful. Okay. Okay, so now I have come, this is actually something I wanted to say last class. So now we have actually completed everything I wanted to say about bosonic and fermionic Fock space creation. So now we have a prescription that starting from the vacuum, just like the harmonic oscillator problem where we move in a one direction, you go from 0 to 1, 1 to 2, 2 to 3 like that and come back by acting one operator. Here you can go, you can collect all the possible points in the corresponding Fock space. In this case, that space is this. According to symmetrization principle, that all kind of numbers, a huge lattice, all direction. In this case, it's a very tiny space because there are not many possibilities. And I have a simple prescription of starting from 0 and going to all the points in that space. But and also some of you please think about this problem. This could be a very creative term paper that think about developing this picture carefully in higher dimension. This will be very nice to do that. Okay.
So why physically we are doing this? It's not clear yet.
What?
Why the particles at the lower levels are affecting the higher level configurations? This is not
No,
clear.
that is because it depends. So there is a difference between these two, right? And the difference we know is that the difference is in shuffling. Right? If I do take that configuration and I shuffle it, and that will pick up a minus sign. So you want to define your F operator in a way that incorporates this fact, right? Because this particular configuration, this particular configuration, and the same configuration where two of them are shuffled, they are not the same according to, because they are fully antisymmetric wave functions, so they are not the same. So this is first quantization notation, by the way. This is nothing but the notation where I write down as this. This is a shorthand of this phi1 r1 phi0. Nothing is there, so there is no need of this. So phi1 r1, and this is phi1 r1. This is no phi6 r1. This is phi6 r1 phi2 r2, and this is phi6 r1 phi2 r2 phi4 r3. So this is this notation. So this one, if it is a fully antisymmetric wave function, if you write all the recombination, and if you shuffle them, then it will pick up a minus sign. So that point has to be incorporated in your fermion operator. So that is all what I did. I just showed you that if I define the Fermi operator this way, it is perfectly consistent with what you expect from symmetrization postulate. Okay, this is just a machinery to develop the fermionic operator. So
yeah, but physically, what is the, like, we are saying that if I don't know if 2 is going to 4 and I am putting a particle in 2. I mean,
that point is also already there, right? So for example, this physically, if you want to think, what operator you can put after these two steps and what operator you can put this after these two steps is already incorporated in the fermionic wave, in the fermionic structure, right? Because it clearly you cannot do a F4 here because that will be double occupancy. You cannot do a F2 here because that will be double occupancy. That the fact that you cannot put two of them at one place, that is already also incorporated in the definition.
Okay.
Because FK dagger on any state will give you 0. Just like FK, double FK on any state will give you 0. Similarly, FK dagger will also 0. Make sense, or you are not satisfied?
Yeah. Not satisfied, but it is making sense.
Okay.
I mean, I don't understand why. I don't understand why. I mean, physically, how can I say that putting 4 when there is 2 is affected by the particle in 2?
Oh no. So physically, that is the whole point. That is, so I'm just repeating Pauli exclusion principle, right?
Okay.
I'm just saying that the fact that what you can put next is dependent on what you have already. That point is not there in bosons. That is all I'm saying.
But why, if there is 4, while adding a particle in 2 is not affected? Because already there is a particle in 4, so the particle I am going to put at 2, that also feels something for that.
So I think you mean to say, so you can put a particle at 2, but the point is the configuration space available for that particle is different. So if you choose to put it at 2, then there is no problem. But if you try to put it at 4, then there is a problem. So what I'm saying, so if you are, so when you are trying to put a new particle, it matters that what particles are already there and where they are. That is all I'm saying, right? That decides that where that new particle can go, and that matters a lot. For example, when you do this problem fermions, right? So you know these filling problems, right? I don't know if you have done that. These I'm telling things a little advanced, which I plan to tell later. So let's say I want to put electrons in the levels, and electrons have spin. Okay. So this point is a little bit tricky. I plan to talk about spin in the next lecture, but let me say that anyways. So let's say I want to put it like that, right? Now, and there is already a configuration like that, right? So this existing configuration tell you the next particle can only go here, the lowest energy configuration, right? So this
is because Hund's rule.
Huh?
It is because of that Hund's rule that the lowest energy state should be.
This is not Hund's rule. This is Pauli exclusion.
Okay.
This is Pauli exclusion principle. Hund's rule is different. For Hund's rule, you have to bring in energetics.
Okay.
Here it is just pure exclusion principle.
Okay.
Make sense?
Yeah, I have to check that. first, then I'll go back to you.
Yeah, but let's not go back. Don't go to anything which is not there in the board. But
Okay.
within the board, if everything makes sense, that is my point.
Yeah, yeah, okay.
Okay. I hope it is not a convincing by intimidation. It's genuine.
No, no, I'll check whatever my problem is in the board and I will go back to you.
Okay. Okay. So now basically this was the plan for the what I wanted to do last lecture. So now today I will go do a little overview of all the things we have learned about multi-particle states, and then I will do some examples. Okay. Or should I do the examples first? Okay, let me do the examples first because things are fresh right now, so better to do an example. Okay. So let's do an example of 4 particles and 6 levels. Just show you how this thing works. So this second quantization language is very important that you pick it up well, because if you do anything in quantum mechanics, many body quantum mechanics, this is the language. Field theory, condensed matter, high energy, everywhere. This is the language which is like, I am right now doing a research problem in which I need to do almost like 50 pages of calculation for one calculation, and that is loaded with this algebra, loaded with this Fermi. I will give you assignments, so make sure to get well versed with this subject. Okay, so let's say I put I have 6 levels. Okay, so for convenience I just made it 6 levels, but it can be anything. So it can happen sometimes. You will see this, there are these problems in physical world problem, that although I know that there are infinite levels in a hydrogen atom or anything else, but it can happen some kind of complex many body effect can make the spectrum like that. As the spectrum is like this and then like this. So these things are the 6 levels, and the next level is far in energy. So then you can effectively think it as low energy problem of 6 levels. So this is the justification of why I am thinking of 6 levels, but it can be anything, any arbitrary finite number. So now this problem can be anything. Let's say it's a particle in a box. This potential could be 6 levels of particle in a box, or 6 levels of harmonic oscillator, anything. This picture is not correct, so it should be far, because we know the particle in a box, the levels are not equidistant, they go n square apart, but in harmonic oscillator they are equidistant. So I have 6 levels and I have 4 particles. So I draw it like that. So now let's say I put the particle, I give you a configuration where I put 2 particles here, 2 particles in level 2. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. 2 particles in level 2, 1 here and 1 in 1, 2, 3, 4, 6, 1 in 6. Okay. So the first quantization notation will be what? The first quantization notation will be, let's say I want bosonic wave function, because of course otherwise I cannot put 2 of them here. Can somebody tell me what will be the first quantization notation? How should I write down the wave function in first quantization? First quantization means what you learned earlier, not Fock space. Just the regular.
Sir, is that particle 3 in n equal to 2 as well?
No, so 3 is in, so this is, I labeled this 1, this 2, this 3, 4, 5 and 6. So this particle is in 6th level. So there is 1 in 2nd level, 2nd is also 2nd level, next one is 3rd level, and then 1 in 6th level. What happened? How come now none of you know? That's what we are discussing for last week.
Phi 1 R1, Phi 1 R2. Sorry, phi
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 two
2
R1,
R1, phi
phi
2 R2, phi 3 R3, and
phi 3 R3, phi 6
phi
R4.
6 R4.
And
And phi 2 R2, phi 2 R1.
all combination, right? All the
Yeah.
permutation.
Sorry, all the power.
Okay. And what is still missing? The normalization. What that should be?
In 1 factorial into factorial by
What is that?
in 4 factorial.
1 by 20,
Yeah,
2
yeah.
24. 2 factorial, 1 factorial, 1 factorial by
2
4
by 4
factorial.
factorial.
Root over.
Yeah.
Right? So if I give you this configuration, you can write down its full wave function, right? Okay. Now how to write it? So there is a shorthand. So let me write it in this way. In this way. So the shorthand is following. I have 6 levels: 0, 2. Do you understand this shorthand? So this shorthand means this. It means I have already taken all the configuration and summed it and normalized it. Clear? Why there is so much silence?
Yes, sir.
Okay.
It's clear.
Now what is the second quantization notation? What is the configuration notation? How do I write it in configuration notation, this particular configuration? Sorry, I this is actually I have written down the answer and then I told you. So this is the configuration notation. So there are two ways of writing it. Okay, one way is to write it as 2, 2, 3, 6. So this is the shorthand for this. This is just to remind you. There will be one at 2, one at 2, another at 2, another at 3, another at 6, and their permutations. This is the old notation or fast quantization notation. I will tell you in a moment that why I am calling it second quantization. You might be wondering, if something is second, then there must be something else is fast. So the fast quantization is the old way, the most traditional way of writing. The second quantization is this, the NK. Everybody is in the same page with these two ways of writing the same thing.
Yeah.
But the second quantization has some information hidden, and that information, as we discussed earlier, second quantization just tell you that. So when you write things in this way, then you know everything that is there to know, right? But it is very hard to manipulate this expression. Actually, if you go to Feynman's StatMech book, they did manipulation of this friend. That's very, very rigorous. But instead, you choose to write it in this way or this way. So this way of writing hides some information, and the information is, what is this phi? Like the phi can be harmonic oscillator, the phi can be hydrogen atom, the phi can be particle in a box, anything, right? That I'm not writing here. And we'll see in some problem that particular information is not necessarily always relevant, unless you want to sketch the wave function. You just want to know which particle is where and where, how do they hop. Okay, so this is the two notation. Now there is a third notation. So how will I write it in this using the creation annihilation? So this is one way of writing, this is another way of writing. How will I write it using creation annihilation? Somebody? What should I act on 0?
F6, F6 dagger.
So I will act D6 dagger, B3 dagger, B2 dagger, B2 dagger.
Sir,
Right?
sir,
Yes.
Sir, what is the convention of that levels? Means 6, 5, 4, 3, 2, 1, or is it 1, 2, 3, 4, 5, 6?
What do you mean by that? This is
Means
one, one, one,
means,
two, three, four, five,
means
six.
where you wrote the n case
Huh.
in second quantization
Yeah, obviously I'm writing it like this.
1, 2, 3, 4, 5, 6.
Yeah,
Okay.
but you can choose the other way also. It doesn't matter. It's just a convention.
Okay.
But once you choose something, you have to be consistent with that.
Okay. Hmm.
Now, what else? Okay. Because of this. Remember this, that VK acting twice will have this NT. So, and this guy is nothing but 0, 0, 0, 0, 0, 0. Okay. So now I can write this state, this particular state in all these different way. And this particular way is very convenient. And that is what I'll show you. Okay. Now everybody is in the same page, that if I want you to write down, give a state, give a problem, you can write down this first quantization, second quantization, all these things, right?
Yeah.
Okay, good. Now let's learn some more manipulations. Okay. Let's learn some more manipulation and see this example. So this actually I thought I'll do an example, but I think I have already done that. Okay, so let's do that again. It doesn't harm to do same thing twice. And you do it because I have already done it. So you should tell me what to do. So let's consider another example. Okay. So the example is I'm taking this 110, okay, and shuffling these two guys. In a purely antisymmetric wave function, that will give me 110. If it is symmetric, it will be plus. Okay. So now can you show this thing will happen using using this boson and fermion? How will you show that? So first of all, how will you go from here to here? It's a two-step process, right? The process is you go from here to here, which means you go to 2, 0, 0, and then you go here. So for that, you have to apply an operator B
C2,
one dagger,
C1 dagger.
B1 dagger, and then B1 dagger will bring it here, and then you
B2.
kill that with B1. So B1, B1 dagger, and B2. Right? This will take you here. But you cannot do that for fermions, right? Because for fermion, there is no such state.
Sir,
Okay.
sir,
So for fermion, yes.
Sir, before going to means 110 to 200, it is B1 dagger B2. Means already annihilation in.
You are correct, correct. Very good that you are paying attention. Very good. So B1 dagger, B2. Right? Right? Everybody in the same page? Now let's say I want to do this for fermion. This is the bosonic root. So try to do all these small examples. I will just show you some, but play with this more. Then you will get more familiarity with this subject. So fermion, what can I do? So let's say I go here. So 101. This is a legal state for fermion. So that is basically exchanging 2 and 3. Then I am going to 011. That is exchanging 1 and 2. From here I'm shuffling these two. And then I can go to shuffling 1 and 3. Okay. So how will I represent such a act? So that act can be represented as F2, F3 dagger, f1, f2 dagger, f3, f1 dagger. If I act this on 110, that will take me to 110. Okay. Now, how do I know that how do I know that? But I know that if I flip these two, I'm going from this to this, right? And the fact that I have exchanged these two particles, that is hidden in this line, because I first exchanged 2 and 3, killed 2, created 3. Then I exchanged 1 and 2, I killed 1, created 2. Then I exchanged 3 and 1, I killed 3, created 1. So let's see how it pans out, how it pans out here. So to do that, what I have to do, I take the f1 in the here, right? I do one shuffle. Now one shuffle means a minus sign. Everybody in the same page? Do you agree that one, if I write this, do you agree that this minus sign will appear? What I did, I took this here. Everybody clear? Why there is so silence and the ESS are all very faint? What is the problem here? Okay, I'm guarding the line. Are you following?
So instead of acting the if operator, then if dagger operator, we can do the opposite as well.
Yeah, correct. We can do the opposite also.
Then
So
they
we
are
will see.
connected with this relation that minus sign will
Yeah.
appear in front.
Very good. We can also do that, but we will show that then it's a homework. Show that they are equivalent. Okay. But let's stick to this one first.
Okay.
Let's stick to this prescription first, then we'll see the other. So do you agree that if I write this, there will be a minus sign? Do you disagree? Since your policy is not to answer, I think a good question is, do you disagree? Then if you say nothing, then that means you all clear. So you have to do one of the two, right? It cannot be nothing. You have to either agree or disagree. So what is your state?
Yes, sir, we agree.
Okay. So this gives you a minus sign, right?
Yeah.
Then you do one more flip. You give you another minus sign. Okay. Then you do another flip. No, now you don't need a flip. You have f1 dagger f1. Okay. So check this. If I take this, if I rewrite this as this form, okay, f3 so let me do it in this way. Let me do it in the way I had done in my notebook. So let's say I move this one and this one twice. So I write f1 dagger f1, and then I have f3, f2 dagger, f3 dagger, f2, 110. Okay. So what I did, I moved, instead of taking the f1 here, I took the f1 two steps here. It is plus sign because it's two shuffle. So now I have left to f3, f2 dagger, and f3 dagger, f2. Okay. So now let's do another shuffle. Let's take this f3 here and f2 here. So then what I get, minus okay. So what did I do here? I took this, I kept this thing intact, and then I shuffled this f3 here. So now I have f3 dagger and f2 here. So then in the next step, I shuffled this. So I picked up a minus sign because it's one shuffling. So then I passed this F2 two steps here, F2 dagger F2. So then it's still it will be a plus sign, but then I took this F3 also in here. Should it be plus sign? Yeah. So then I took this F3 here. So now this step is nothing but F3 dagger. So I create a F3 here and I kill that F3 here. So I end up with a -110. So what I'm trying to say is that this F, the
Sir, in
algebra
that,
of F, yes.
sir, in that last line, if we do F3 dagger F3, it will be 110.
No, whatever you do, it will be 110. You can do F3 dagger F3, but for that you have to do the following: 1 plus F3 dagger F3, right? You cannot randomly do that because it's the same object. So when you do that, because notice what is that, F1 dagger F2 is this, but F3 dagger F3, because they are same, when you index are same, then it is 1, right? So these will give you the 1 and this will give you 0. Understood?
Yes, sir, I am trying to.
Okay, so try to show this, that this thing acting on 110 will give you -110. So the fact that you have shuffled these two particles, that information is already there in the commutation anti-commutation algebra. Okay, so internalize this algebra. Then in the next class, I will do some revision. And the downside of your of taking the class in Blackboard is that there is no note, there is no board work PDF. So I hope you have copied everything properly, and try to do this algebra. And if it is still unclear, you can ask me in Piazza or something. Okay, that is all for today. There is a quiz up, so answer that quiz in next 10 minutes or so. And this is a short quiz. It's a very short quiz. You can write it probably in a few. It's based on last week's thing. It's a counting problem. Can you see the quiz?
Yes, sir. It's there.
Okay, good. So the purpose of many quizzes is that to distribute the performance, because some of you might not be doing well in one quiz. So the many quizzes will make sure that unless you are doing very bad throughout the semester, it won't be very bad for you. So don't worry about doing bad in one or two quiz. There will be many quizzes and all will be scaled to 20 marks. So one or two doesn't matter, but make sure you are not doing bad in many quizzes. Okay, that's all for today.
Do we have
Yeah.
to write an explanation?
Sorry?
This quiz, do we have to write an explanation about this question?
Yeah. Write an explanation. Just write a outline that how did you do this? How did you get that number? You must have done something, right? Either you used a formula or you did some counting, right? So whatever that is, write that. You can take a picture of your notebook and put it, or you can write it in the comment box. If you just write the number, one can get that number from someone else also, right? So I want to know that you have used your mind to get that number. That's the whole point. You might have got it from a book, doesn't matter, but you know what it is. It's your awareness. It's not somebody told you it's some number. Okay, that's all.
Sir,
Yeah.
sir, in that blank form, is only option 1 is visible, or
No, blank form is, so I have removed the blank form because I don't need it anymore.
Okay.
Because I realize it's the same thing, and earlier I needed it to know who is doing it honestly, but now I don't need it. It's just extra confusion. Okay, let me wipe the board. Meanwhile, I guess you are all busy with writing that, so probably will not ask anything. So this, try to do this exercise, that 110 goes to -110 because of shuffling, that this whole information is already encoded in the anti-commutation of F. Let me wipe it later. Let me wipe this side first. Okay, that's all. So I'll just log out.